Good evening, everybody. Today we'll be talking about secondary stage. This is our lecture 9 and computer architecture in electrical engineering and computer engineering. Without further ado, let's go ahead and start on this. Say, so let's go over the contents of it. So talking about the contents of the of our today's lecture, we are going to be talking about an introduction to a secondary stage, disk organization and performance, the floppy disk details, the hard disk mechanism and performance, disk interfaces and caching, disk arrays and RAID, and as well as summary of all of this. Next up, we have introduction to secondary stage. What's a brief introduction for it? There's a primary and there's a secondary stage. We already went over the primary in our previous lectures, going over RAMs, random access memory, read-only memories, hard disk, non-volatile and volatile memories, and etc. However, today we're going to be focusing on secondary stage. Under that falls the hard disks, the non-volatile memory, and their larger capacity of storage. Over here on our left side, we have a diagram showing the difference between the primary memory and the secondary memory. Shown over here, primary memory is like the read-only memory or read access memory. They're not very handy when they want to be used, and they're not able to be like relocated from one place to another as easy as CDs, DVDs, hard disk, and floppy disks. In today's lecture, we'll just be understanding how all of this works out. So next over here, we'll talk about disk organization and performance. So under disk organization, there's the falls the track, sector, cylinder, and the cluster. As shown over here in the diagram as well, it shows all of that. The track is pretty much the ring of the data. The sector is the subdivision of the track. The cylinder is a set of tracks across the platter, and the cluster is just a group of sectors. Performance metrics, though, we have a capacity, access time, and interfacing standards. The capacity, it depends on the amount of data stored. The access time, it's the speed of accessing the data. And the interfacing standards are methods for connecting storage devices. That was for disk organization. That's how disk organization, what it has, what's inside of it, and how it works out. As next, we're going to be talking about floppy disk details. So floppy disk details. As the components of it, there's the magnetic material coding, the index hole, and the sectors storing the 512 bytes. However, it can vary, it can have more bytes. Just depends on the type of floppy disk. Over or less bytes. Over here we have like all the components. I'm sure that we're not required to know all of these components, but those are also good to know. What a floppy disk have, it has an HD hole, a casing, a liner, a hub, a magnetic disk, another liner. But our main things that we need to focus about in this case are like the magnetic disk, because this is where everything is stored pretty much. The invention of the floppy disk was it was licensed by IBM, and it was invented by Dr. Nakamatsu in 1952. The encoding techniques for it were FM or MFM, which means frequency modulation or modified frequency modulation. The frequency modulation has just a simple single density disk, as the modified one was double density, fewer transition, and it had a higher density, which was like the better version of it, pretty much an upgraded version of the regular floppy disk. Next over here, we're just going to be going through some hard disk mechanism and performance. Hard disk components. There are solid metal platters. There's fly heads. They have a rotational speed that goes between 3,600 to up to 15,000 RPM, which is pretty amazing, honestly. If you could take into mind. It has like similar metrics as the flying disk and as the I'm sorry, as the floppy disk and as a regular disk. However, over here, there's like a seek time, rotational latency, and as well as the transfer time. It's organized in a similar way as well as the others. Sectors, clusters, encoding, and it has multiple encoding methods, such as the modified frequency modulator as well over here. Over here on the left, we have a diagram showing the components of a hard disk, which is an air filter, a platter, a spindle, actuator, which are pretty similar to how a disk works or a floppy disk. At the end of the day, they all fall under one thing, which is our secondary memory criteria, which we are discussing today in our lecture. Next over here, we'll just go over the disk interface and their caching. Over here in this diagram, it's a little bit extra, but we can show how under RAID, which we'll get more into in a second in our next slide. But under RAIDs, we can see how SATA develops, and what are SATAs? SATAs are pretty much smaller cables. They're hot swapping and they have high data transfer rates, as is the SC there, and they're considered disk interfaces, by the way. As for the SCSI, it connects multiple devices. The IDE connects multiple disk drives. So they all fall under one part, which is how the disk interface at the end of the day. But the SATA is well known because it is pretty much like our main brain in this case. It transfers the data. It has the hot swapping. It has cables and all of that. As for disk caching, it's temporarily stored in a disk in a RAM to reduce access time, and then it navigates and it goes into a native command queuing, which optimizes whether a read or a write order to reduce head movement of the disk. Nevertheless, over here we're going to just be going over some the topic of disk arrays and RAID. So disk arrays, it's pretty much a combination of multiple disks in one system. It provides redundancy and scalability. The RAID levels, though, this is where it falls. This is where like those fall under the disk arrays. The RAID levels, there's this RAID 0, 1, 5, and 6. The 0 consists of stripped disks, no fault. But the RAID 1 has a mirrored disk with high redundancy. The 5 has a block level stripping with distribute party, and the 6 has a blocked interleaved with double party. As for redundancy mechanisms, there are data replications and parity protections. Nevertheless, over here, we just have a small example of in the case study. It says over here, calculate the average latency for a disk rotating at 3600 RPM. This is how we calculate it using a regular like rotations per second, and then we just like calculate the revolution, and latencies in a very similar way. Anyways, this was for today's lecture. We're just going to conclude it right there. We just went over some key concepts about secondary storage and their disk and their techniques and how we can understand their mechanisms and interfaces. I hope this was beneficial, and I hope to see you soon again. Thank you. Goodbye.